am often not late. And I'm glad that I have always tried to come on time. But this, I had two engagements. This morning I was in meeting of Swami Chapter, next to center from there, and everyone contributed. Okay, so my colleagues have already discussed with you yesterday, on Saturday, that this concept of pulse NMR spectroscopy is of fundamental importance in NMR spectroscopy. It is central to the modern NMR. That has been a departure from conventional continuous wave NMR spectroscopy, pulse, Fourier transformation. And that is not only the methodological changes, but also conceptual changes. So remember, I wish you to kindly recall that in continuous wave NMR spectroscopy is very plain and simple, to be honest. It's the same machine as like IRUV, except that it has, and when it is magnet, there are two energy states for dipolar nuclei, and then you take radio frequency, it's absorbed and recorded. Can't be simpler than that. If that was an NMR, there was no need of me interacting. We could have very easy life and no issue. But unfortunately, that has fortunately some issue. It really happens to change in a major way. Now, NMR spectroscopy is different. And remember, the need is the mother of innovation and innovation. And that every development which has taken place or which takes place in science lead to another need. Every research paper gave an answer of a question and create new questions. Similarly, in NMR spectroscopy, NMR was developed, but then there was a new need. People have identified new weaknesses, trying to improve it. So I told you this miserable life of people who were recording NMR in 1960s, spending all of their life of recording NMR, slowly tuning radio frequency, and as soon as radio frequency matches with the normal frequency of a particular proton, then there was a signal absorption recording, and this was taking forever. It was taking literally hours. So it's not a very time efficient method. It was also at the same time a method which was inherently insensitive because there's just one NMR spectrum which you recorded, and there were plenty of noises. There were plenty of noises and less of signal. So then somebody in 1949, as soon as the NMR was developed, thought of why do we really need to? I mean, everything started from this interesting question. And the question was, why do we really need to excite every proton or synthetic, whatever you're regarding, one by one, right? Why don't we just excite them together, right? And let them relax. So instead of recording absorption, we just excite them together and record their relaxation. And we assume that relaxation would be different, right? Absorption is different, relaxation will also be different. And I often give this example since centuries, that you have three protons, three of you. Okay? You are these three, your CH2, your OH. Okay? So two Egyptians and went Yemen studying along, and a pulse, a powerful pulse, a brief powerful pulse of radio frequency, translate, such as a bulldozer come, okay, slowly hit them, and they will all be on the ground, excited, not in a very good sense, but excited. They will be all at the same time on the ground, right? But do you really assume that they will get up on their feet at the same time? Why not? They are very strong people, right? According to their inherent absorption and realization. So maybe perhaps I don't know. That will be stronger one.
How we can explain excitation out of the same as everyone has spatial need to go to the.
Anyway, respond to this very interesting question of how can we really excite all of them together? Is this possible? It's a question, logical question. Magnetic field. To get magnetic field now, I want to take magnetic field out of my life. Magnetic field is there, omnipresent, ever present. You can't do anything. You cannot do anything without magnetic field, so forget it. Right? Magnetic field is there, already there. Now we're talking about excitation. And question is, how can we excite all of them at the same time? Radio frequency pulse, of course. But his question is, how can we use radio frequency pulse to excite all of them together? This is exactly, you take radio frequency window, a radio frequency pulse, which has all relevant frequencies required to excite all of them. Again, understood. So instead of exciting one after the other, you take a window. It's not a radio frequency single, but a radio frequency burst. Right? So you take a burst of radio frequency which carries various radio frequencies, and you give them like this, pulse. You give them like this, a short burst of radio frequency, very powerful. So they all are excited. Okay. When they all are excited, you disturb thermal equilibrium. And like anything on the face of the earth, the system will try to achieve a thermal equilibrium. It would like to go back to its original stable equilibrium position. And for that, it has to lose energy, right? And that is called relaxation. In NMR spectroscopy, relaxation is recorded. Okay. Understood? Not absorption anymore. Okay. The good thing is that now you can keep hitting these three boys. They get up, you hit them again, you get up, you hit them again, you get up. And every time by camera, you record who is in what time they are getting up on their feet. Right? Understood? Exactly this happens. So instead of one miserable episode of recording a spectrum, slowly sweeping the radio frequency, you give pulse, you excite them together, you let them relax. Relaxation is recorded by detector. As soon as they achieve thermal equilibrium, we give them another pulse, and you keep recording. What a beautiful concept. Think of it. It's just absolute beauty. Because now instead of one NMR spectrum, you have thousands of NMR spectrum. Sky's the limit. You can have as many NMR spectrum as you wish to. You just overlap them together, and you would have random noises, fixed signals. noise is always there. You know, when you have electronics of the kind of NMR, you're just completely mind-blown. You go to NMR machine, if you try to dissect NMR magnet, you would see just coils and coils and coils of everything. Radio frequency is generated by coils. Detection is carried out by coils. Everything is electrical, magnetic, and all that. Noise are natural. So noise is small little signals everywhere, right? Like when you turn on the radio, it's never a very clear voice. You try to tune it, right? So noise are very random, and more NMR spectrum you accumulate, the better would be signal to noise ratio. But signals are right on the same position. Noise are random. Noise becomes baseline, and signals are always there. So improve signal to noise ratio, and signal to noise ratio is sensitivity. That deserved, in my opinion, several Nobel Prizes. Unfortunately, they can give one Nobel Prize. Okay, and that Nobel Prize was given to Professor Richard Dawkins because he was the one. It was not his original idea. What he was able to do was to translate that idea on Albert Hahn into a practical, adoptable, affordable technique. So think of it. Before this first software-based sensitivity enhancement method, everything was expensive. You need to develop large and large magnets and all that. It just cost you a fortune. It just cost you so much money that you can't afford it. Here, the man has carved a method which doesn't really require expensive hardware. It's just a state of mind. You know what he has done? He said, okay, just excite them together, record the relaxation, keep doing it. You would have so many spectrum, combine them together, noise is random, it goes into the baseline, signals are at the same place. You would have better signal noise ratio. Sensitivity enhanced, not because of hardware, but because of an application of software. And thus, this is one of the most seminal methods ever developed in the field of advanced. Okay. So I told you that pulse power define which nucleus you want to detect. That you know already, right? You know that for every element, there is a different frequency range. So you can select pulse of your choice as you detect your elements. Pulse width define. I mean, this is the width which he was asking. You know, width radio frequency. You know, so instead of a single radio frequency, you're using a radio frequency width, and that radio frequency width covers or select. You have this choice of exciting all of them or exciting only one, right? In NMR, you would see that many methods in which excitation is selected, selective excitation, but it's not the point we confuse ourselves in this, okay? And also, the pulse duration, that is something also extremely important, and that I left you last time with and I left you that bulk magnetization vector, which I suppose you all understand, that represent the Boltzmann distribution. The axis, the difference in population between low energy state and high energy state. Very tiny little difference in population. But that is crucial. That is critical. That is what you can measure, because that is the one which absorbs radio frequency energy. So think of it that you can bulk magnetization vector, which is called M naught, representing net magnetization difference. You can rotate that, right? If you give a pulse duration which brings this magnetization vector to XY plane, it's called 90 pulse. If this duration of the pulse is more than that, then you can bring it to 180, right? So this is called pulse duration. You can select, and again, amazing that there is no other technique in the world which you can play with everything. Think of how many choices you have in NMR. There is absolutely nothing like this exists on the face of the earth. In any NMR spectroscopy, you just excite and record. Right? Here, you have a choice of selecting an element. You have a choice in that element to bring the magnetization vector anywhere on this three-dimensional cartesian by selecting a particular direction. And I'm sure my colleagues would have probably told you about writing down. Okay, so if this is the magnetization vector, M naught, and this is the radio frequency pulse provided, if it is from the X side, remember that radio frequency pulse must be perpendicular to magnetic field. So it go like this. Where? Y. If your radio frequency oscillator, your thumb is on Y, it goes to minus X. If it is on minus X, it goes into minus Y. Yes, like that. You know, it is so amazing. Isn't it? You're not excited. I don't see any excitement, any happiness, any joy on your face. I'm so surprised because even today when I teach NMR spectroscopy, my hairs, little hairs are just, it does make you excited. I'm sure you're excited. You're just pretending not to be excited. Okay, so this tremendous capacity of being so selective that you can place this magnetization vector anywhere in X vector. Now, think of it. You have your longitudinal magnetization. It's called longitudinal. When it is from Z, it's called longitudinal. And you bring it to XY plane. It is called transverse magnetization. I will not really use Z or whatever. I will use longitudinal magnetization excited to transfer plane, transverse XY plane. XY plane. You brought that to XY plane. You brought it to XY plane, what will happen? You brought this magnetization vector on XY plane of your own choice, wherever you want to, right? Because the detector is on XY plane also. What will happen? Ab kya hoga? What will happen? Do you think that this magnetization vector will sit and enjoy there? No? What it will do? Goes back to relax, yeah? Thermal equilibrium. But will it go like this? No. It will resonate, with the same precision frequency. It will precess on XY plane, and like a reverse umbrella, it goes up right? Like this. Will go up, right? So it is on XY plane. Unfortunately, I cannot rotate my hand in 3 dimension, but I'm sure that you can understand that it is along the magnetic field. It is moving, and then it is slowly losing the angle and going back to the original position. This is the relaxation. This relaxation is required. Think of your detector. Assume that you are a detector here. You are a detector here on the XY plane. And in front of you, this bulk magnetization vector, all of us haven't come. And that magnetization vector is oscillating with the angular velocity of precision frequencies, depending on how many photons there. Your detector will detect, but that signal will reduce because magnetization vector is going back to thermal equilibrium. Okay? It's like this. It will not be there forever. It has to go back to thermal equilibrium. And when it goes to thermal equilibrium, if you are a detector looking into your eye, you see this magnetizing vector going up, right? You would see a full signal and you see a little less signal because detector will see only what is present on XY plane. As it is going up, it's decaying. So the word which was used was, once you bring magnetization vector on XY plane, it decays. There's a full signal, and then it goes back to longitudinal position. It's called free induction decay. This is what you get from NMR. This is what, if you go and get your NMR sample done, they will give you a small, or they will email you the data of free induction decay. So you don't get any spectrum. You don't get any absorption. You just get that free induction decay. And that is now question is, I mean, you excited this by giving a radio frequency burst. Okay? And this energy has to go somewhere. The energy has to go somewhere because it is now in high energy state. In order to achieve thermal equilibrium, energy has to be lost, right? That is called relaxation. Where this energy will go? It's very tiny little energy. To
the RF also, the energy in the RF radio frequency, the radio.
this is what initial scientists thought, that energy would be released as radio frequency. No radio frequency was ever detected. You excite that is a non-radiative energy loss. No radiation. Energy is lost in a very subtle manner. Where this energy will go, how does it get there? Mechanism of transfer of energy, and how long does it take to lose the energy? These are enduring questions in NMR spectroscopy. Where the energy will go, how this will go, and how long it will take. Okay? That determined the time of free induction. Okay? So relaxation is an extremely important phenomenon in NMR spectroscopy. The system which you have excited need to relax back to thermal equilibrium. What are the mechanisms through which it loses its energy? there are so many of these relaxation mechanisms, but two are most important. One is called T1, spin lattice relaxation, and the other is called spin relaxation. Okay, so we are now talking about relaxation, very important, because relaxation, if your signal never relax, you would never be able to have the second pulse. Second pulse has to be given when longitudinal thermal equilibrium is achieved. Relaxation is important, and understanding relaxation is also very important. But that gives you a profound understanding of how these nuclei relax. Some relax slowly, then the other. Like three of them will stand up on their feet differently, right? So this nuclear spin will have a different relaxation time, and they will have a different relaxation mechanism. So there are broadly two important relaxation mechanisms. One is called spin lattice relaxation, longitudinal relaxation, T1. A big T1. Remember, there is a small T1 also, which will come and we'll start discussing two-dimensional. Right now, it is a big T1. The energy goes into environment. And what is the environment of molecules? Solvent, right? Everywhere solvent. It is dissolved in solvent. It goes to lattice, It goes into environment. The other mechanism is that they don't really lose energy to environment. They lose energy, they transfer energy to each other. So Adil holding the hand and getting energy from the hood, right? So this energy transfer from between the spin is called spin-spin relaxation. Most important is spin lattice relaxation. That is most important. 90% of our brain and our methods are based on spin lattice relaxation. Because that is a real loss of energy. Right? Adil holding Mahmood's hand is not a loss of energy. They're just transferring energy to each other. It's not a loss of energy per se, it's not a true loss of energy. So relaxation is very important, and that is the spin lattice relaxation. Based on relaxation, free induction decay are recorded. So if we have three signals of ethanol, okay, and you excite them together by using a pulse, radio frequency pulse for short duration, 90 pulse. Duration is defined as the resulting angle. Actually, it is in seconds. You know how many seconds you need to excite them. But you talk about end result, 90 pulse, 180 pulse. You don't explain that into time. You know why? Because different for different elements. You cannot say 3 seconds, you get 90 pulse. Of course, in C13 NMR, you can't get that in. So you don't really talk about the seconds you need. You just talk about the end result of 90 or 180. Okay. So 90 pulse or whatever. Now in 90 pulse you're given, there are three spins who are excited at the same time, and they are now on XY plane. They will start processing on XY plane. First of all, they will split. Because these are three individual spins. There are going to be three vectors. Okay? And detector will see three vectors. And then they go up like a reverse umbrella. This is barish mein umbrella nahi khul jati. They'll go back, right? So this now detector will detect free induction decay. What's called free induction decay? You excited them by energy, radio frequency oscillator is off, done, finish, and collapse them up. Okay, now this three vectors on XY plane are free from any influence. No induction, nothing like this, nothing except this ever-present magnetic field. They are not influenced by anything. They are free to relax back. And this relaxation is called decay. Because I don't really see any appropriate word. If I'm a detector, for me, the signal is decaying. Right? Because it's going right from a full three signals. Smaller signal, smaller signal, smaller signal. Okay. So the free induction decay is non-radiated. No radio frequency is detected. What actually happened is that when these radio frequency, when this magnetic factor passed in front of detector, it created a little electrical impedance, a little disturbance in the electrical coils of the detector. So the signal is non-radiated. And this is absolutely unimaginable that people could have understood that so easily. Radio frequency goes in, radio frequency never come out. This is the physics of weak forces. You know, many things unique in NMR spectroscopy. You give radio frequency, no absorption, unless you place them in magnetic field. In this case, you give a radio frequency never come out. It converts into electrical impedance. Tiny temperature change, which nobody is able to measure so far. There is no thermometer developed which can change this tiny little temperature change due to radio frequency absorption. The only thing which you can measure that if you are a detector, okay, and if I am passing through you, radio frequency pulse, I'm in front of you. You see me full, okay? Then it goes like this on XY plane, right? So you see me like this, like this, like this. But at the same time, I'm lifting from the floor, going up. So you see my knee like this. Okay. Three signals of SMR. This is starting point, right? Full signal here. Adil is seeing me right in front of him. I'm going away from him. I'm going to minus 5. I'm going to minus Z. I'm sorry, minus X. I'm coming back in front of him. I'm going again to minus 5, minus X, Y, plus X. One, not visible, right? It's called free induction decay. And this is electrical signal. Every time passing through this, the detector is looking into signal. And this is time, you know. This is not any frequency, it is time. So assume that you have three, assume you have three, assume you have three signals of ethanol. You would have three like this, right? The difference would be because they have different regulation mechanism, they have different energy absorption. The three FID would be different, right? So the signal is in time domain, not in frequency domain. How long it takes to have a full decay of methyl? How long it takes to have a full decay of CH2? How long it takes for full decay of OH? Time, not frequency. Yeah. Yeah. I mean, when you will get up from the ground, there's time, right? Isn't it? How long other take will take? Maybe you take 1 hour. Who knows, you know? So this time is your signal in NMR spectroscopy. FID time is your NMR spectrum. You can't you don't like time. How would you see? If you have three signals, maybe you can see. But if you have like 3,000 protons, God, you know, it's going to be. And that is the reason why strong computational development was required to decipher such effects. Now think of it, time has to be converted into frequency. Because you, from 1940s, are habitual of looking into frequency signals, not time signals. Such thing is not very exciting for you. I don't know where we have this. You know, if you have like 3,000 of them, it's not very exciting for you. It's just black lines.
How long this time? About how many seconds?
It depends on your energy.
How many?
You tell me how long you're going to take to get up from the ground.
5 years.
You know, this is, but I'm sure that you're different from one who.
Yeah, okay, but I'm talking about how long it takes this time? How long? 5 seconds.
Okay, that's a good question. Think of for different elements, this is different. It is generally in seconds. Okay. And in order to have about 1/3 of the signal going going back to the propellant to longitudinal magnetization, they measure that. I can't tell you because every molecule is different. I mean, I can't give you time, but it is generally in seconds or even less than that. Okay. For C13, it is in several minutes. And some C13, such as quartic carbon, it takes infinite time because they have no mechanism of relaxation. They have no neighboring proton. Their relaxation is very slow. So this time is dependent on the type of elements and type of protons you have. And of course, that is dependent. Everything you need to relate it with electrons. Everything you need to relate it with precision frequency, Raman frequency. Never forget those concepts because eventually this is a mechanism of recording that. Eventual purpose is to record precision frequency. Now, by doing this relaxation, you're recording a spin friction decay is a time domain signal. It is a time domain signal. Okay? You need to convert that time domain into frequency domain. It's called Fourier transformation. You use mathematics called Fourier transformation. So you convert time into frequency. Now collectively together is called pulse Fourier transformation NMR spectroscopy. First FT NMR. And that is the reason why Richard asked for a Nobel Prize. But he didn't really give an abstract idea of exciting them together. He practically converted it. Okay, if you excite them together, how would you convert that signal? Right? Would that mean to have so many lines like this? And how would he convert that time into frequency? That is the Fourier transformation. Or built in. This is called, there was a continuous wave NMR spectroscopy. It is called pulse Fourier transformation. And I'll give you the advantage of that. Number one, signal to noise improvement. That enable you to use a small sample and get a good spectrum. Right? Second, see the team which was a very insensitive nuclei to begin with, now you can measure it. Because you're not really measuring one spectrum, but you're measuring literally thousands of spectrum. Sometimes they run their experiment overnight. Overnight, the same thing happens. Right? So it enables you to increase the sensitivity. It opens the door for you to detect the signals elements which have never been detected before. So this was a revolution. Theoretically and conceptually, it's so different. Because over there was a straightforward absorption. Here you're talking about excitation of all of them. Recording relaxation not as a frequency, but as a time. Converting that time into frequency. So how different NMR become? They become a very different animal altogether from the animal which was built and nurtured in 1940s. Any question?
It's complicated.
It's complicated, yeah. NMR is, NMR is like a roller coaster. Sometimes but it's still digestible, right? Life is going to be more exciting and challenging for you after a few days. Because all of this will be translated into experiment. Why we are learning all of it? Why would you need to learn all relaxation or excitation or FIDs? Eventually, because you would design your own experiments. Okay?
Yesterday we had workshop from music. Because presentation some slides, we working on solid state NMR for nitrogen. I mean, if we have something like my project in membrane, solid, how we can take NMR?
Okay, so you can record NMR in liquid. Okay. It was also possible to record in NMR of solid samples. And that's called, remember when I was telling you about the development of NMR spectroscopy, I told you that back in 1990s, solid state NMR was developed with magic angle spinning, MAS, SSMAS. And the name got longer. Solid state magic angle spinning, pulse Fourier transformation. Mind-boggling. Solid state NMR is essentially the same. The difference is that probe has to be different. Remember that you're not only putting a tube, you're putting only a capillary with little solid sample. And even that has to be tilted to a magic angle in order to avoid T1 elevation. And you can record this, but this is not the time to discuss solid state. If I do that, I lose you. There are a lot of devices and escape and I don't know. And I really wish you to stay with me till the end. My end or your end. Thank you. I love this. On Sunday, sure.